Graph the following functions. All right, in example A, we have f of x is equal to x squared minus 5x minus 3. We would love it if this function was already in this form here. If it was in that form, f of x is equal to a times x minus h squared plus k, then we'd be able to see what the vertex is right away. We would know exactly what the a leading coefficient is, although I think here it's going to be 1. I think we can see that part at least. But, we would know those things that would allow us to graph the function very easily. However, in the current format, we don't know that directly. Now, I did give you a little shortcut here, which tells you how to find the x-coordinate of the vertex using just the b and a terms. And once you have the x-coordinate of the vertex, you can then take that answer and then plug it into the function and determine what the k, y-coordinate of the vertex is. So you can get the vertex that way without doing what I'm about to show you. The reason why I'm showing you how to do it the long, hard way is because in class, your professor may force you to do it the long, hard way. So a lot of professors want to see you complete the square on the quadratic in this format in order to demonstrate that you have the ability to do this. All right, so it's a skill that I guess is useful, and so that's why they want you to do it. However, remember that you can always check your work by finding the h-coordinate of the vertex by just doing negative b divided by 2a. And remember, the h-coordinate is the x part of the vertex. Okay, so let's go ahead and just do the complete the square step, and then again, we can confirm that our answer is correct using that shortcut. Okay, so let's look at the complete the square idea here. We're going to be completing the square only on one side of the equation, which makes it a little bit different. So we'd want to make sure that leading coefficient is 1. The number in front of x squared has to be 1. It is 1 here, so we don't have to do anything there. All we're going to do then is just kind of take the x parts and then leave a little space and then put the constant a little further away, if that makes sense. Then from there, I'm going to sort of think about this as something that I want to be a perfect square trinomial. And the way we're going to do that is we're going to do the complete the square piece, which is to take that middle term here, find half of it, and then square it. So half of negative 5, right? And then square it. All right, so if we square that fraction, we're going to end up getting positive 25 over 4. And it's this that we would have to add in here to complete the square. So we'd literally say, well, plus 25 over 4. Now here's where it gets a little bit tricky. We're only doing this on one side of the equation, so you can't just add something to your equation and say, oh, it's the same equation. You can't do that, right? You can't just add 25 over 4 and say it's the same function we started with. So we've got to make sure that we only add 0 to the function overall. So that means we have to add outside of that parenthesis we put a minus 25 over 4. And this makes sure that we're compensating for the fact that we just added 25 over 4. So we're taking it away at the same time. It means that the net effect is 0. And that's what we need to have happen. Okay, from there, what we want to do is to factor that perfect square trinomial that resulted. And I don't know if you remember this from before, but I think I told you once before that the factoring here will just come from this piece here. So in other words, you'll take x and then just put that minus 5 halves there and then squared. So you actually, before you squared that piece to complete the square, that's actually what you get in the parenthesis when you do end up factoring the trinomial. The reason why I mentioned to do that is because it's a little hard maybe to do it when you have fractions. People get a little confused, but you can confirm that that's in fact correct. If you expand it out, you'll get the right answer. All right, from there though, then you have this minus 3 minus 25 over 4. You just need to clean up that arithmetic a little bit. Let's put 3 over 4. So if it's 3 over 1, to make that into a fraction that has a denominator of 4, we'd have to multiply the 1 in the denominator by 4. That means we need to multiply the 3 in the numerator by 4, which gives you 12 fourths. Then you have 25 fourths. So altogether then the function ends up being x minus 5 halves squared. And then we have negative here. They're both negative, so they're both going to be over 4. So we keep the common denominator. And then 12 plus 25 gives you 37. Okay, so that is your new function. It's basically the same function we had before, it's just rewritten, right? And the reason why that's helpful is because now I can tell you where the vertex is. I can tell you that the vertex of this parabola is basically at positive 5 halves. Remember that we take the opposite sign of the piece that's in the parentheses, right? So 5 halves for the x-coordinate of the vertex, and then negative 37 over 4. Not the best points for a vertex, but they are what they are. And then from there, we can just plot a couple extra points to make the graph go. I'm just going to, because we've gone through plotting points before in other videos, so what I'm just going to do is basically plot the vertex roughly where it is on our grid. And then because I know the parabola will open up because the a term out in front, the leading coefficient is 1, I know it's just going to open up kind of in a standard width. So let's do that very quickly to finish that first example here. I'm going to draw a grid system. Okay, so I've drawn my grid system, and then I'm just going to kind of turn our fractions into decimals here. So 5/2 is the same as 2.5, right? And then, 37/4, well, 36/4 would be 9, so that'll be 9 1/4 or 9.25. Okay, so there's our points, and again, remember that's negative 9.25 because the 37/4 is negative. By turning them into decimals, it's just easier to put them on our grid here. And then I'll need a little bit of space to do this. So I'm going to actually make each of these 2. So I'll make that 2, 4, 6, 8, 10, so that'd be like the position 10 on the axis there. And likewise, 2, 4, 6, 8, 10, and 2, 4, 6, 8, 10, right? So just to kind of give us a reference point for my grid system. Okay, so from there, let's go ahead and plot the vertex. So 5.5 is 2.5, so maybe we're looking at something just after the 2 there on X, and then down to 9.25, so maybe about there is where our vertex is. Now remember, because the leading coefficient is +1, we're going to open up from that point, so basically we're going to have something like that, right? Whether it's wide enough or too wide is, again, we just kind of approximated what it would look like. That's basically what the graph looks like. If you want to get a couple extra useful points, you can then solve for maybe the x-intercepts. That'd be very useful. And the x-intercepts, remember, just set the function f of x equal to 0 and solve for the zeros, and that will tell you basically where those occur. You could actually do that in the initial function by using the quadratic formula on it. So let me just take a quick second to show that how that would be done. So I'm going to take a here, basically, x squared minus 5x minus 3, and I'm going to go ahead and set it equal to 0. So if I wanted to find where those intercepts occur, I would have x squared minus 5x minus 3, that's our function, equal to 0, and I would solve that. Now, are there any factors of 3 that will subtract to give you 5? I don't think so, so it's not factorable, this equation. So I'd have to use maybe the quadratic formula on it. All right, so to use the quadratic formula, it's just negative b, or in other words, negative 5, that's positive 5, plus or minus the square root of b squared, so that'd be 25 if you square the b term, minus 4 times the a term times the c term. And then from there, we just kind of put all that over 2 times the a term. All right. And then from there, you'd have 5 plus or minus the square root of, inside the parenthesis, you'll end up having 25 plus 12, right? So 25 plus 12 all over 2. And then, of course, that'll be 5 plus or minus 25 plus 12 is, again, 37. So the square root of 37 over 2. And if you get the decimal versions of those two numbers, that's where those x-intercepts are occurring. That's where the graph crosses the x-axis. So we have 2 solutions, basically. You could work those out. If you wanted to see what they are, these are basically approximately equal to 2 solutions. The 2 solutions are negative 0.54 roughly and positive 5.54. All right, so those are the 2 solutions, essentially. All right, so just, approximated where they're at. And so our drawing, probably we're a little bit off on our drawing since I crossed it over, it looks like between 6 and 8. I probably crossed my axis here at about 7 when it really should have been about 5.5. Either way, so it's approximately drawn correctly, but obviously I could have been more precise if I had put those intercepts in just so. All right, but basically that's the idea behind graphing example A. So let's go ahead and look at example B then. So for example B would be the same thing. Because we already showed the complete the square step here, of course, we could just jump right to using that shortcut, getting the x-coordinate of the vertex, then plugging that in so we could get the y-coordinate. But I'm not going to do that because I want to show you again another example, just to show you what happens when we have a leading coefficient that isn't 1. So when you look at this example B, you see that the leading coefficient isn't 1, so that's going to make it a little bit harder. What we're going to do still is, isolate the x pieces, right? And kind of push out the constant a little bit, right? And put this sort of in parentheses, knowing we're going to try to make that into a perfect square trinomial. But the catch is here is that we want to have a coefficient of 1 before we start this, so that x squared term cannot have a negative 3 in front of it. We're going to have to factor out a negative 3. So if I factor out a negative 3 of that, what's going to happen is the x squared basically loses the negative 3, and I'll have to divide the 4 by negative 3, right? And the reason why I have to do that is remember that factoring is really just division. And so if I write that a little more properly, I would say x squared minus 4/3 x, right? Space, and then negative 2. Okay, so now we'd actually do the complete the square step. Same thing as always, we take half of the middle term and we square it. Well, half of negative 4/3 is basically the same as multiplying it by a half and then squaring it. So if you do that, we'd end up having negative 4 over 6 squared, which remember can be reduced as negative 2/3, right? Because 2 goes into 4 twice, goes into 6 3 times squared. And then finally, that'll end up giving you 4/9, right? Now, the reason why I care about this kind of arithmetic is, remember, this will get us our factoring, right? Right before you squared it, that tells us how the function will factor, or how the quadratic will factor. All right, so let's go back to this 4/9 here. If I put the 4/9 in here, that means I've added 4/9 here, right? So you might think, oh, then you're supposed to do what? Minus 4/9 here to make up for it? That's actually not correct in this case. And the reason why it's not correct is because the 3 here is going to end up multiplying inside of here, right? The way you have it written, that 3 is going to distribute. And when it distributes, it's going to hit that 4/9, making it actually negative 12/9, right? So in other words, minus 3 times 4/9 is going to actually give you negative 12 over 9. So that's really what you're putting there on the function. When you put that 4/9 in parentheses, you're actually putting negative 12/9, really. All right, so that means that on the other side, we've got to put positive 12/9, right? We got to put the opposite of what's happening inside the parenthesis. Okay, so that means we're going to put a plus 12/9. And this way, the negative 12/9 and the positive 12/9 will cancel out, giving us a result of 0 there. Remember, we can't just add a number arbitrarily to the function. That's not okay. All right, so remember what we said before, that the factoring would basically end up being x minus 2/3, right? So when I factor that trinomial, it'll be x minus 2/3 squared. And then we have the minus 2 over 1 plus 12/9, right, to deal with. All right, so we got to get a common denominator of 9 there. So if I multiply this guy by 9, I multiply the top by 9 as well, I'll end up with negative 18, right? Because negative 18 over 9 is negative 2, and then I'll have plus 12/9. And so then that means that the total arithmetic there will give you negative 6 over 9, which can be reduced. So we'll end up saying that that will be what? 3 goes into 6 2 times, right? So we'll have minus 2 and goes into 9 3 times, negative 2/3. All right, so our final function, factored and simplified and all that, is minus 3x minus 2/3 squared minus 2/3. All right, so we finally got that into the form we wanted. All right, so let's go ahead and identify the vertex then. The vertex is going to be equal to positive 2/3 comma negative 2/3, right? That's the h and k pieces for the vertex. All right, so we have to plot that on a graph, and then we're going to deal with the fact that the leading coefficient is actually negative 3 here, right? Negative 3. That means it's going to open down and it's going to be particularly skinny. All right, so let's go ahead and create a little rectangular coordinate system to work on. And this time we could do something like, for example, 1, 2, 3, 4, right? So 1, 2, 3, 4, making every space roughly count as, every space half of a step, right? Okay, so 1, 2, 3, etc., right? 1, 2, 3. Okay, now from there, the vertex will be at 2/3 on the x, so not quite all the way over, and then down, not quite all the way down, so maybe right about there. And then it's going to be skinny, opening down, right? So we'd basically have it opening down, and then, kind of being a little skinny. Now, I'm going to draw this piece of it, and then what I'm actually going to do is get one extra point. Let's get the y-intercept. The y-intercept is very easy to find. All we have to do is let x be 0, right? So let's go back to our original function and let x be 0 in that original function. If we let x be 0 in the original function, remember we had negative 3x squared plus 4x minus 2, right? So this was our original function. It was negative 3x squared plus 4x minus 2. Now, if we actually plug 0 in for that x value, we'll end up losing this term, and we just get negative 2. So in other words, right at this point on the axis, we're going to hit that with our graph. So remember, plug x equals to 0 to get your y-intercept. And the reason why I wanted to do that is because I knew that this graph, I could see that it was going to hit the y-axis nearby, and so it'd be helpful to know precisely where it hit it. That makes our graph a little more perfect, right? Because we know that it's opening down, we know it's a little bit skinny, and now we can see it also hits right at the y equals 2 point, or negative 2 point on the y-axis. And that's it.